So we want to find f of x given that the derivative of it is this with this initial condition. So we essentially want to take the antiderivative here of this function. And so why don't we apply term by term integration? So let's take the antiderivative of each of these pieces. And so this would be 3, and then x to the 2 plus 1 over 2 plus 1 plus 4 times x to the 1 plus 1 over 1 plus 1 plus 1 times x to the 1 over 1, because 1 had like x to the power of 0. So you probably could have done this without me doing it the fancy way, but let's just see what this becomes. This becomes 3x cubed over 3 plus 4x squared over 2 plus x plus c. So this is just x cubed plus 2x squared plus x plus c. So yeah, I understand that you probably just could have gone from here to here, but I wanted to do these fundamental steps just in case, all right? Now, the only thing we need is to find the value of c, which is why they give you this initial condition. You see this guy here, this is the antiderivative. So if anything, you can call this f of x, all right? Because this was the antiderivative or the integral of f prime, which is just f. But now you have to find the value of c. So what you do is you plug that in for x and you plug that in for y, where of course this is just y. So the 5 goes in for the left-hand side, completely replaces it, and the 1 goes in for all the x's. And so this will quickly tell us the value of c, because 5 equals 1 plus 2 plus 1 plus c. And so this tells us that c has to be 1. And so the goal was to find f of x. And so we have, this is the original function right here, because this respects the initial condition, and the derivative of this is in fact that there. Number 2, find L6 for this from there to there, and then find the exact area. So maybe we can make a diagram here of sorts. This would be at 3, 6 with a negative orientation. So look, this equation here, you can rewrite this as f of x equals negative absolute value x minus 3 plus 6, where the vertex of this absolute is at 3, 6. You take the opposite of that and you keep that. That's where you find the vertex of this absolute value, which is going to be an upside down v at 3, 6. So at 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. At 3, 6, 1, 2, 3, and you go up 6. That's the vertex of the upside down v, the absolute value graph, and it has a negative slope of 1. So these rays would go down 1 over 1, down 1 over 1. So it goes down like this at 45 degrees. And we are interested in L6 from 0 to 6. So what I'm going to do is I'm going to draw these vertical beams. So let's go vertical through at 1, at 2, at 3, at 4, at 5, and at 6. We have these vertical regions. And we want to use the 6 left. The L means for left. You want to use the 6 left points. So I want to use this one. 1, 2, 3, 4, 5, 6. So I'm counting from the left. 1, 2, 3, 4, 5, 6. If this had said R6, like right, then I would have gone from here. This would have been 1, 2, 3, 4, 5, 6. So that's the left endpoints. And so now what you really want to do is make a table of values. And what you want to use for x is the 6 left endpoints. In this case, 0, 1, 2, 3, 4, 5, and 6. 0, 1, 2, 3, 4, 5. And actually just 0, 1, 2, 3, 4, 5, right? Because this is 0, 1, 2, 3, 4, 5. Because from 0 to 5, that's 6 items, the 6 left items. Now what you do is you take 0 and plug it in for x into the original equation. If you plug in 0 here, if you work out the math, it should be positive 3. If you plug in 1, it should be positive 4. If you plug in 2 into there or into there, doesn't matter, it's the same thing. You should get about 5. If you plug in 3, you're going to get back 6 because that's the vertex. If you plug in 4, it starts to count back down and you get this here. And so now what we do is we're going to build rectangles, the 6 left rectangles. So go to a left point and move to the right. Go to a left, move in. Go to the left, move in. Go to the left, move. Go to the left, move in. Go to the left, move in. So now what we have are these 6 rectangular regions. And these 6 rectangular regions are an approximation for the area that is underneath the upside down blue V. So now we have to find the 6 areas of these rectangles and add them together. But look at the first rectangle. Each of these rectangles has a width of 1, right? Because they're all 1 unit in width. Now, what's the height of this first rectangle? The height of it is 3. All right, that's the purpose of using this number. So this first rectangle here, it's the area of it is base times height, but the base is 1 and the height is 3. So this is like 1 times 3. The next one also has a width of 1, but the height of the next rectangle is 4. So you have to find the areas of all 6 of these rectangles. I'll just go down here. It's a little clearer. So it's 1 times 3 plus 1 times 4 plus 1 times 5 plus 1 times 6 plus 1 times 5 plus 1 times 4. It's always 1 because for this problem, the width of these rectangles is 1. And the heights of them happen to be the y values, which is why these y values appear as the heights of these rectangles. If you just compute this and add them up, what's that going to be like? Was that 10, 18, 18 plus 9, was that 27? It looks like it's 27 square units. So that's the area. So they said find L6 for this. We did this method with left triangles. That's the area. Now here they want you to find the exact area. So what we can do is we can look at the model again, and let me just sort of kind of duplicate it. The only thing I really want to emphasize is probably this point here, and maybe this point here. So based on the previous graph, this point is at 0, 3. This one was at 3, 6. And this one was at, what was this one at? This one was at 6, comma. If you plug in 6 into there, you're going to get 3. So we want to find the actual area of this because this rectangular concept, that's just an approximation. So it says you find the exact area using a known formula. So what you can do is, I mean, there's many different ways you can do this. You can look at it as 2 trapezoids, or you can look at it like this. You can look at it as this red triangle and this rectangle. It doesn't matter how you look at it, you'll get the same number. So let me look at this problem as the rectangle and the triangle. So for this rectangle, it's a rectangle. This width here is 6 and the height is 3. For the triangle above it, it has the same base as the rectangle, 6. But the altitude is how far up it goes. Well, if it goes from 3 to 6, that means the height is 3. So the area of this one is 6 times 3, which is 18. And the area of a triangle is 1/2 the base times the altitude, which is going to be, was that 9? And so you can add together the 2 areas, 18 plus 9. So the actual area is 27 square units. So sometimes the approximation, L6, R6, whatever, sometimes they're accurate. In this case, it's perfectly accurate. Sometimes these approximations are no good. But it just worked out that this method gave us the actual exact area.